Okay, now I know that I love a lot of these theorems involving circles and chords. And all of them are like my favorite. But let me show you my ultra, ultra, ultra favorite, and I'll tell you why. Here is the statement of the result. It says that an inscribed angle subtends a semicircle if and only if the angle is a right angle. First of all, the if and only if means that an inscribed angle subtends a semicircle, then the angle is a right angle. But also, the other direction is true, which is that if we have an inscribed angle that's a right angle, then in fact we subtend a semicircle. A lot of words. What does it mean? Let me show you. Bottom line, if you put in a diameter somewhere, anywhere at all in a circle, and you pick any point you want on the circle, and you produce the two chords, one from one end of the diagonal, the diameter up to that point, and the other point from the other chord from that point out to the other side of the diameter, then you have actually produced some kind of inscribed angle. And since, in fact, you are on two sides of a diameter, that means that you subtend a semicircle, that the arc that you've swept out is a semicircle, half of the circle. And since that, you know, is going to be 180 degrees, half of that is going to be 90 degrees. This is such an important fact. First of all, I think it's beautiful. But secondly, this is so useful. Whenever you're dealing with circles and you've got things going on and you're either trying to prove something's a right angle, or you're kind of hoping something's a right angle, or you don't know what to do, but if something were a right angle, things would be good, it's almost always this theorem. Now, don't tell anyone, but this is the trick to do a lot of the circle questions that we're going to be faced with. Anyway, I love it. Let's take a look at some examples where you can see this theorem in action. So, this question asks us to find W. Find W. When you look at this picture, it looks like we don't know too much, just that this angle is given by 11W plus 24. But if you look closely, you see that there is the center of the circle. And so I see that, in fact, this is a diameter. This is a chord going to one end of the diameter. This is a chord going to the other end of the diameter. I see, therefore, that this arc is a semicircle. And so I know that its measure is 180, which automatically tells me that this has to be a 90-degree angle. It's a right angle. So therefore, this thing equals 90. And so now I'm home free. Love this theorem. So if we subtract 24, I see 11W equals 66. And so W, when I divide through by 11, equals 6. And so therefore, W equals 6. And that was the question. Find W. W is 6. Isn't that great? Let's look at another example. Here, the question is to find the angle JKM. So I want us to figure out the measure of this angle. How can we possibly do that? Well, let's think about this. That is actually an inscribed angle, which has JM as its associated arc. So we know that the measure of this angle is half of this. But what about this angle right here, which is 5x minus 4? We know that's an inscribed angle that's associated with the same arc. So in fact, its measure is half of this. So this has a measure that this is equal to half of this. This is equal to half of this. This is the same. So therefore, these must be the same. And so what I see here is I can set up an equality which says 4x plus 3 equals 5x minus 4. If I bring the 4x to this side by subtracting 4x from both sides, I see 3 equals x minus 4. If I add 4 to both sides, I see x equals 7. That's not the answer, though, because I want to find this angle. So I plug in 7 for x. So 7 times 4 is 28, plus 3 is 31. And so I see that this angle is 31 degrees, and that's the answer. So the measure of angle JKM equals 31 degrees. Again, you can see the beautiful structure of chords and interior angles. And in the very special case, when in fact this line actually is a diameter, we know that interior angle has to be 90 degrees.